Hi again, everyone. So this is going to be a lesson on matrix inverses for linear algebra. And where we left off last time was we talked about matrix operations. We know how to add matrices, subtract them. We know how to do scalar multiple of a matrix. And now we know how to do matrix multiplication. And we also learned a couple of other quick little things like transpose and trace. So the inverse of a matrix is another, you could think of it as another matrix operation, and it's so important that it gets its own section. So let's get started. So in the last lesson, we spent a lot of time building up some definitions and notation, terminology, properties. We had a lot of stuff to talk about before we could actually get to the main topics. This time, we can just go straight to the main topic, the inverse of a matrix. Definition: the inverse of A denoted A with a little -1 up there is the matrix such that A times A inverse equals I, and A inverse times A equals I, period. And we understand that, well, actually, there's a couple of things that we understand from this definition. First of all, I is the identity matrix. And we didn't specify what size it is, but we also didn't specify what size A is. Anyway, let's say a couple of things about this. First of all, in what sense is this an inverse? Maybe you're used to thinking of inverse functions. You have a function that might have, might have an inverse, and the two functions kind of undo each other. Well, this time we're thinking of a matrix, which is like a grid of numbers, and we're saying that it has an inverse such that when you multiply them together, you get the identity. So really, when we say inverse, we're talking about a multiplicative inverse. This is the multiplicative inverse of A. And you multiply them, you get the identity in either order. So, a couple of remarks. First of all, first remark, A must be square. Why does it have to be square? Well, look at what we wrote above. A times A inverse equals I. We know that the identity matrix is a square matrix. So the only way this is going to work out is if A is also square. Second remark, not every square matrix has an inverse. Exclamation point. Okay? Not every square matrix has an inverse. That's actually going to be kind of one of our topics that comes up again and again, is whether or not a matrix is invertible and what can we infer from that. If A inverse exists, we say A is invertible. I think I just used that word. So let's actually make this a term. Invertible. And another remark, this lesson focuses on 2x2 matrices. Okay, now the above definition, this is something that we could talk about for square matrices, but for now, to get started, we want to focus on the smallest possible case. I guess you could say 1 by 1. you know, maybe we could talk about those, but those are not very interesting. 1 by 1 matrices are not very interesting. So 2 by 2 is the smallest case we can look at that is actually interesting to look at. So, example, if A equals this matrix 3, 1, 4, 2, then A inverse, by the way, I didn't really put this on my list of remarks, but I guess I should just acknowledge one thing. This is not an exponent. We're not raising A to the -1. I know in the last section, towards the end of the video, we had a definition that was A to the K, where we talked about how you could do A squared, you could do A cubed, right? And you could write A squared, and it means A times A. However, this is not an exponent. This is notation that we use to indicate the inverse of a matrix. Just like if you wrote, you know, F inverse or sine inverse, you know, you put a little -1 up there, it doesn't necessarily mean reciprocal. It doesn't mean 1 over A or anything like that. Okay? Now that I got that out of the way, I'm going to tell you what the inverse matrix is for this case. I'm not telling you yet how I found it, but I'm going to tell you that this one is invertible, and this is what its inverse looks like. How about that? If that's the matrix A, then that is its inverse. We can verify. Even though I didn't tell you how I found it, we could verify that it works, because from the definition, it needs to be a matrix that when you do A times A inverse, you get I. When you do A inverse times A, you get I. So let's just quickly check that. We know how to do matrix multiplication now. So if I do A times A inverse, let's for this first one, let's write out the pieces. Okay, I actually wasn't planning on it, but let's write out the pieces. So what do we do? 3 times 1 plus 1 times -2. 3 times 1 plus 1 times -2. Up here, we do 3 times -1/2. This is good practice for you, too. You know, you can work this out. Plus 1 times 3/2. It's 2 by 2, the result. 4 times 1 plus 2 times -2. And then over here, we get 4 times -1/2 plus 2 times 3/2. So let's make sure I did everything right. What do we get? 3 minus 2 is 1. What do we get over here? -3/2 plus 3/2 is 0. What do we get here? 4 plus -4 is 0. And over here, -2 plus 3 is 1. That's what we expected, right? We expect the identity matrix. This is the identity. So yes, that checks out. And it should also work in the other direction. And for this one, I'm not going to write all of the little in-between steps. I'm just going to tell you that you can verify. Do this for practice if you'd like with matrix multiplication, but you do, in fact, get the identity. Okay? I still have to tell you, if I give you a matrix, how do you find its inverse? And how do you find out if it is invertible in the first place? All right, let me tell you some stuff. I actually had some of this stuff in my notes as kind of optional, but I want to cover it. So I think this is going to be useful. So fact 1, in the previous lesson, the video right before this one, we had the property IA equals A equals AI for any n by n matrix A. Okay, we had a list of properties of matrix operations, and one of them is that the identity matrix works in this way. That's really what makes it the identity matrix. When you multiply I times A, it doesn't change A. What I want to tell you as a fact is, in fact, I is unique in this sense. No other matrix does this. I is the only square matrix that is going to have this property for every n by n matrix A. So there's only one multiplicative identity, and that's why we call it the identity matrix. There is only one. It can be different, you know, it could be 3 by 3 or 4 by 4 or 5 by 5, whatever side, but there's only one for each n, I guess you could say. So that's a fact that we might have been kind of assuming that, but this might be the first time that I actually wrote it out explicitly. I is the only matrix that does that. All right, fact 2. I just want to remind you that up at the top of this page, I wrote, in the definition of inverse, we said A inverse equals I, and we said A inverse A equals I. You know, to be an inverse, it has this and this. What I want to tell you now is that the first one actually implies the second one. That if the first one is true, then the second one is also true. And that means that up here, when I did this work to kind of verify, to check to see, is this actually an identity matrix, I checked both directions. I did A inverse, I found I. I did A inverse A, I found I. But in fact, we only had to check the first one. Because if the first one is true, it's going to automatically imply the second one. And I'm going to prove this to you. Fact 2. I'm going to write a short proof of this. Proof of fact 2. First of all, let's suppose A inverse equals I. Okay. What we're going to do is multiply both sides. Multiply both sides by A on the right to get A inverse times A equals IA. Next, we use the associative law and fact 1. First, I'm going to use the associative law on the left-hand side. By the way, let me take a step back for a sec. Let's just review what we're doing here. We started with the hypothesis. When I said multiply both sides by A, we're allowed to do that as long as we do it to both sides, but we have to specify, are we multiplying by A on the right of each side or on the left of each side? That makes a difference, right? With matrix multiplication, that makes a difference. So we said multiply both sides by A on the right, and I put A to the right, and I put A to the right. Associative law on the left-hand side of the equation means I can move the parentheses around. So I can move the parentheses like that. That's by the associative law. And I'm going to use fact 1 to say that IA is equal to A. Now, do you see the rest of the proof? I think there's only one more sentence. Everything we need is on the screen right now, in fact. But I need to write one more sentence to wrap this up. All right, what we have right now is A times this thing in parentheses equals A. We said in fact 1 that I is unique in this sense. There's no other matrix that does this. So if we have A times a matrix equals A, then the thing that's in parentheses here must be I. I'm going to say then by fact 1, we must have the thing that was in parentheses must be I. End of the proof. That's a cool little proof, isn't it? I guess I didn't really prove fact 1 to you. I didn't really prove that I is the only identity matrix, the only one that works that way. I'm not sure if that proof of fact 1 is in the book or not. Okay, so the point of this is that it seemed like there were 2 conditions for being an inverse, but in fact, you only really have to check one because it implies the other. Also, you might be wondering, does this also work the other way around? Can you say that, is this like if and only if? Could you say that this implies this? The answer is yes, although we haven't proved it. I wonder how, can you think of how would you prove that the second condition implies the first condition? I think I don't want to give that away. I'll tell you that the proof would be similar to this. Maybe think about it on your own sometime. But yes, the idea is if you have one of those properties from the definition of inverse, it implies the other one. Okay, now we've talked about the definition of inverse. We had a couple of remarks. We had one example where I gave us the inverse, and you might be wondering, how did I find it? So this is going to be our big question, is if we're given a 2 by 2 matrix, and because it's 2 by 2, I'm just going to label the entries as A, B, C, D. Okay? You could label them A11, A12, etc., but let's just call them A, B, C, D. What is A inverse? And for now, we're going to focus on this 2 by 2 case, and we'll see whether or not the inverse exists as we go through this process. To work on this question, to work on answering this, let's suppose A inverse does exist, and that, it is also 2 by 2. And let's give these entries a name. So I'm going to call them W, X, Y, Z. Then we want to find W, X, Y, and Z so that what is it that we want to be true? We would like W, X, Y, Z times A, B, C, D. We would like this to equal the identity. Now, we're supposing that A, B, C, D were given to us, but that W, X, Y, Z are not. So there's kind of 4 knowns and 4 unknowns. Are we going to be able to find them? I mean, really what we want to find is formulas for W, X, Y, Z. We'd like to find formulas for those 4 things in terms of the 4 things that we know. A, B, C, D are given constants. Can we find formulas for the other 4 in terms of the known things? So let's see what happens when you multiply this out. Like left-hand side, this times this, what do we get? So we could do WA plus XC, right? WA plus XC, except instead of writing WA, I'm going to write AW. We kind of prefer to write the letters in alphabetical order if it's a real number times a real number, A times W instead of W times A. And I'm going to write CX instead of XC. All right, in the next entry, we would do WB plus XD. I'm going to write that as BW plus DX. Down here, YA plus ZC. So I'm going to write AY plus CZ. And in the lower right, YB plus ZD. I'm going to write BY plus DZ. And we want that to equal 1, 0, 0, 1. Now, if the left-hand matrix, this 2 by 2 matrix, equals the right-hand matrix, all of the corresponding entries must be equal. So, for example, AW plus CX must equal 1. BW plus DX must equal 0, and so on. So you could say that maybe we could write them all out as like 4 separate equations. We'd have 4 equations with 4 unknowns. Here's what I'm going to do. I'm going to write that the first row of the left equals the first row of the right. That gets me that AW plus CX equals 1 and BW plus DX equals 0. And we're going to look at those two. The second row, by the way, you could say that's AY plus CZ equals 0 and BY plus DZ equals 1. Do you see why I separated them out into a system of 2 equations and another system of 2 equations, instead of writing it as just a big system of 4 equations? The reason why I split it up is because this 2 by 2 system has 2 unknowns, W and X. This 2 by 2 system has 2 unknowns, Y and Z. So it works out pretty conveniently. We could just focus on the WX part of it and the YZ part of it. Let's focus on this part, this system, okay? From this system, if we were to try to solve this system, like remember, we're assuming that A, B, C, and D are given constants. It's W and X that are kind of the unknowns that we would like to solve for. So if I wanted to treat this as a system and maybe like solve it with an augmented matrix, my augmented matrix would look like A, C, B, D, 1, 0 to try to solve this. Can we do Gaussian elimination on this? I mean, we don't have the... Maybe you feel like if we had A, B, C, D, it would be easier, right? But we're trying to come up with a general formula. So let's leave them as letters. I'm going to show you that we can row reduce this anyway. All right, so first of all, we'd like to, eliminate some stuff and get a 0 to show up. So how do we get this B entry to be a 0? All right, what I'm going to do is I'm going to multiply row 2 by a constant. And the constant that I'm going to multiply row 2 by, first of all, let's copy row 1. I'm going to multiply row 2 by the constant A over B. I didn't give myself a lot of room here. A over B. Why am I multiplying by A over B? Because watch what this turns the matrix into. That makes this A, and, well, we could write this one. Maybe instead of writing D times the fraction, maybe we write A D over B. Okay. Um, is this helping us? Well, now I have an A and an A, so if I would like to row reduce and I would get one of these entries to be 0, I could do that by adding a multiple of one row to another. So what I'm going to do, I think if we add -1 times row 1 getting added to row 2, all right, I'll write this one. Add negative row 1 to row 2. So row 1 stays the same. Let's give ourselves plenty of room. A, C, 1. What happens to row 2? This entry becomes a 0. That's the main reason why we did that. What happens to this other entry? AD over B needs to become AD over B minus C. And then what happens to the 0? The 0 becomes -1 because we added -1 to it. Should we keep going and try to do Gauss-Jordan elimination and like get rid of that C would have to become a 0, right? I'm going to say let's not do Gauss-Jordan elimination. Let's say we got it into triangular form, right? Triangular form. And let's just use back substitution and let's work from here. Let's not do any more row reduction steps. All right. We'll get a fresh sheet of paper. But we're going to refer to what we're looking at here. Okay, what does row 2 say? Back substitution, usually you start with row 2, right? Row 2 says that AD over B minus C times, let's remember the system that this came from had a column where the unknowns were W and a column where the unknowns were X. This is coming from the X column. So row 2 is telling us this about X. Can we solve for X? Yeah, I think we could solve for X in terms of these other letters. So maybe we say X is -1 over AD over B minus C. Did we just do what we wanted? We said a few minutes ago that we wanted to find W, X, Y, and Z, and we would like to find them in terms of A, B, C, D. So we kind of just did it for one of them. We found X. I think we could fix this up a little bit. Let's, I don't like having a fraction inside a fraction. So let's multiply by B over B, because I think that's going to help clean this up a little bit. And that's going to make this -B over AD minus BC. Do you think that looks nicer? I like this better. I don't like having the fraction inside the fraction. I prefer this. All right. Of the 4 things that we were trying to find, we just found one of them. And if you understand this far, then I think we don't need to go through the steps of all the other ones. I think I can just tell you. I hope everyone's all right with that, but I would like to just tell you, what do you get for W? What do you get for Y? What do you get for Z? So I'm going to say, use similar steps to find. By the way, we just found X. You know we could use row 1 to find W, right? And then how would you find Y and Z? You'd have to use this system and do the same sort of thing on this system to find Y and Z. What you would find is that W equals D over AD minus BC. X we just found, I'm going to copy it down, minus B over AD minus BC. You would find that Y is -C over AD minus BC, and Z is equal to A over AD minus BC. So there is kind of a similar structure to all 4 of these. They're not just completely random, right? let's summarize this result. And let's summarize it, and let's see if we can find a more convenient way to write it instead of these 4 formulas. So result, if A equals A, B, C, D has an inverse. If there's an inverse, it is this matrix. We're going to write it in another way after this. So if the inverse exists, that's what it is. I'll put a comma after that instead of a period, comma, which can be written as, what if we say all 4 of those entries have the same denominator? So maybe we would say, let's just write A inverse equals 1 over AD minus BC times. What happens if you pull that out? If you pull that out, what are you left with? D minus B minus C A. Maybe that's a nice compact way to write it. Maybe that's a little bit nicer. Let's put a box around this. It's pretty important. There's something else in this result that I also think is important, and it's the word if. I'm going to underline the word if. Okay? Because we said not every matrix is going to be invertible. So if it's invertible, that's what the inverse is. This ADBC showed up in a bunch of places, and it has a special name. The number AD minus BC is called the determinant of A. We write det A equals AD minus BC. There's also 2 other ways to write it. Determinants. You can see that the determinant kind of plays a role in the inverse. Determinants are going to be pretty important for us. So another way that you could write it is you could write det and then just kind of write out the whole matrix. Instead of capital A, you could just write that. And the determinant of that matrix is AD minus BC. So the determinant of a matrix is a real number, right? AD minus BC is real number minus real number. So just some number. Or another way that we write it, this is going to be new notation for us. Because determinants are going to show up pretty often, sometimes instead of writing the word det, so instead of writing determinant, bracket, A, B, C, D, close the bracket, sometimes we do this. So take a look at that. It looks like I wrote the matrix, but I did not write square brackets. I just wrote vertical bars. And if you just write vertical bars around the entries of a matrix, it means you're taking the determinant. It's a nice shorthand. When you have a matrix and you want to take the determinant of it, you just write vertical bars around it. Now, keep in mind that I want to remind you that earlier I said this lesson focuses on 2x2 matrices. Everything we've done here is for 2 by 2 cases. If you had a 3 by 3 matrix, you can't use this formula, right? This formula is not 3 by 3. There's still kind of the open question of what about 3 by 3 and 4 by 4? Like, what about, do they have inverses? Is there a formula for them? Is there such a thing as a determinant of a larger matrix? Because so far we've only said how to find the determinant for 2 by 2. Well, the answer is yes. The determinant and inverses, they exist for those larger cases, but it's not the same formulas, so we're going to have to talk about those separately. Now, you might look at this and you might say, it seems like we're making some assumptions here, because what if this denominator is 0? AD minus BC is a real number, right? What if you had a number for A and B and C and D? What if you had numbers that made this denominator equal 0? Then you'd have 1 over 0. Well, it turns out that A inverse exists whenever the determinant of A is not 0. Okay, so yes, it is a problem if that determinant is 0. If the determinant is 0, then the formula for A inverse has a 1 over 0 in it. So if the determinant is 0, then the matrix is not invertible. Or if the determinant is non-zero, then the matrix is invertible. All right, pretty cool. Pretty cool. All right, everything we just did on this page, I know that we wrote our result and we wrote it in a couple of different ways. I actually think that it's important enough that I want to summarize it again. Let's just get everything in one place. Summary. If the matrix A, which is 2 by 2, A, B, C, D, has determinant not equal to 0, then A inverse is equal to 1 over the determinant of A times D negative B negative C A, period. If the determinant of A equals 0, then A is not invertible. And I guess just, what do we want to say this? Do we want to say, remember, determinant of A is AD minus BC. Okay, now we have everything all in one place. Let's put a big box around it. That's pretty good. Pretty good summary. I'll give you a chance just to make sure you have that down. So it seems that there are two important things to remember about this, two kind of formulas to, I guess. You have to remember the formula for the determinant, AD minus BC. I'm trying to say it over and over so that hopefully you remember. Maybe look at A. Look at A and think AD minus BC would be like the upper left times lower right minus upper right times lower left. So there's this kind of crisscrossing that's happening. AD minus BC. Maybe that helps you remember it. The other thing you need to remember is this, like, what's going on with these? So the way that you could remember how A goes from A inverse is like D negative B negative C A. If you just want to remember those, that's fine. But I think one thing that you could do is you could say, it looks like the A and the D swapped places, and the B and the C stayed where they are but became negative. Does that help? A and D look like they swapped. B and C stayed where they are but became negative. I don't know if that helps or not, but that's a good summary of matrix inverses for the 2x2 case. Okay, so I'm going to have a problem for you to try next. Let's apply this. And if you're studying for this class, what we just wrote above would be a good thing to put on like a flashcard or something to make sure that you know that. Here, I'm going to give you a question with 3 parts. So wait till I write all of it. Let A equal 2, 3, 4, 5. B is going to be 1, 3, 2, 6. And I is always used for the identity matrix. We know what the identity matrix is in the 2x2 case, but I'm writing it again anyway. All right, 3 parts to the problem. Is A invertible? If yes, find A inverse. Is B invertible? If yes, find B inverse. Is I invertible? If yes, find I inverse. So I'd like you to pause the video for a minute and give this a try. Okay, according to what we've said above, we can answer the question of is a matrix invertible or not by finding its determinant. So let's start with part A. What is the determinant of A? I'm going to use this notation, the vertical bar, 2, 3, 4, 5. So this says that I'm finding the determinant. This equals a number, right? And the number that this equals, the AD minus BC is going to be 2, 5 minus 3, 4, right? So 2 times 5 minus 3 times 4. 10 minus 12 is negative 2. Negative 2 is not equal to 0. So A is invertible. So let's continue. Now that means that we could go ahead and continue and find the inverse. Negative 2 is not 0. Okay, so A inverse is equal to, the formula that we wrote above says that you start with 1 over the determinant. Well, it's useful then that we already found the determinant, right? 1 over negative 2 times the matrix. You know how up above in the summary we wrote it as like D negative B negative C A? So in this case, that's going to be, I think of it as the 2 and the 5 swap places. The 3 and the 4 stay where they are but become negative. This is a scalar times a matrix, and we should go ahead and do the scalar multiplication. Negative 1/2 in front of this matrix, go ahead and multiply it out. So you wind up with negative 5/2, positive 3/2, 2, negative 1. Okay. All right, so that's it for part A. Yes, it's invertible, and that's the inverse. For part B, let's, before we start trying to find the inverse, let's find the determinant. You notice that if the matrix is invertible, you're going to need that determinant anyway. So you might as well just go ahead and find it first. So let's just go ahead and find it. Determinant of 1, 3, 2, 6 is going to equal 1 times 6 minus 3 times 2. Uh-oh. This is 6 minus 6. Right? This is 0. The determinant of b equals 0, so b is not invertible. That's the end of that problem. That's the end of part B. That's the end of the story. You can't find the inverse if the determinant is 0. That means that there's no matrix. You know, remember what an inverse means? You take your matrix, here it is. Take your matrix times its inverse and it gets you the identity. Well, there is no inverse for this one. So there is no matrix that you could multiply this by that's going to get you the identity. Part C. Let's find, okay, this is the identity matrix. Let's find the determinant of it. Let's do this the same way we're doing the other ones. So the determinant of the identity is 1 times 1 minus 0 times 0. So this is 1. All right. It's not 0. So I is invertible. I inverse, oops, I didn't realize I'm going off the bottom of the page. This is what I've been writing. I did the AD minus BC and I got 1. It's not equal to 0, so I is invertible. I inverse is 1 over the determinant, which we found to be 1, times, all right, let's think about how these pieces swap around, right? You know how I've been saying that it's like A and D trade places with each other? Well, the 1 and the 1 swap places with each other. The B and the C stay where they are but become negative. What's negative 0? Negative 0 is 0. So look what happens here. We get I. Get I. The inverse of the identity matrix is itself. So we're done. We answered part C. We found I inverse. It is I. And I'm just going to say off to the side, this makes sense because I times I inverse does equal I. So I is its own inverse. Pretty cool, pretty cool. By the way, if you wanted another practice problem, one thing that you could do is you could go back to near the beginning of this lesson, that first example that we did. In that first example, I gave us A and I gave us A inverse. And originally, I didn't tell you how I found A inverse. Well, now you know how I found it. I found it like we just did in that example problem. So as another practice problem, if you want, go through the steps of finding A inverse and make sure you get the same thing I got. But let's move on. So we know how to find the inverse of a 2 by 2 matrix if it exists. We know about the determinant, and I have a little bit more terminology to tell you. The phrase A is non-singular means A is invertible. Okay, non-singular means A is invertible. A is singular means A is not invertible. Okay. What's another way that we could think of this? Another way we could think of this. How about in terms of the determinant? I'm going to write this in blue. A is non-singular, means A is invertible, means the determinant of A is non-zero. I don't know. We put that in quotation marks if we want. I'm putting quotation marks around all these phrases. This phrase is equivalent to this phrase, is equivalent to this phrase. The determinant being non-zero means it is invertible, means it's non-singular. And then down here, these are the same as saying that the determinant of A is equal to 0. Keep in mind that this is all assuming that A is a square matrix. In particular, I said this lesson was focusing on the 2 by 2 case, but we're definitely focusing in on square cases. We will get to some larger ones before this video is over. We'll get to at least the 3 by 3 case. All right, so that was a little bit more terminology. So if we understand matrix inverses, what are they useful for? Let's start looking at what are they useful for. So Theorem 5. Theorem 5 says if A is an n by n invertible. What's another name for that? I could say non-singular. If A is an n by n invertible matrix, then for each B, that's a vector B in Rn, the equation Ax equals B. Ooh, that sounds like stuff that we've talked about before. The equation Ax equals B has the unique solution x equals okay, I haven't told you what the solution is yet. But we're saying if A is invertible, then for any vector B, the equation Ax equals B has a unique solution. That's already, like, we could put a period here and that would already be a useful theorem, I think, knowing that it has just one unique solution. But this theorem goes further and actually tells us what the solution is. The solution is A inverse times B. If you look at Ax equals B, do you see how we go from the equation to the solution? Let's talk about this a little. Why is this theorem true? I'm not doing kind of a full rigorous proof of this, but I'm going to give you kind of a sketch of a proof. I'm going to say given Ax equals B, you could multiply both sides on the left by A inverse. You see how that gets you from the equation to the solution that we said? When you multiply this on the left by A inverse, you just wind up with I times X, which is the same as just X. So the left-hand side just becomes X. The right-hand side becomes A inverse B. I'm going to say see full proof in the textbook because I did omit some details, but this is the main idea. So this means, I'm going to write this. I think this is important enough that I'm going to write it. So this means, this theorem means that a system, a linear system, having solutions is connected to whether or not A is invertible. We've seen that in Theorem 5. I mean, it says if the matrix is invertible, then for every B, the equation has a unique solution. But maybe there are going to be some other theorems that tell us about a connection between a system having a solution and a matrix being invertible. You know, I'm just going to say more about this soon. And I'm going to put this in parentheses. This is just kind of a side note. But I'm trying to convey to you that knowing whether or not a matrix is invertible is going to have uses to solutions to linear systems. By the way, we know a quick way to tell whether or not a matrix is invertible. Check the determinant. Is it 0 or not? All right, so Theorem 6. Theorem 6 has 3 parts to it. Part A. If A is invertible, then so is A inverse. And the inverse of A inverse is A. This is something that we might have been kind of thinking about even though we hadn't said it yet. You know, if a matrix is invertible, are they inverses of each other? You have a matrix and you have its inverse. Are they inverses of each other? And the answer is yes. They are inverses of each other. And that seems like it makes sense if you think about how we typically use the word inverse in mathematics, like when you've learned about the inverse of a function. When you have a function and an inverse, they are inverses of each other. So yeah, matrix and an inverse are inverses of each other. Part B, if A and B are n by n invertible matrices, so they're both invertible, they're both the same size, then so is AB. Their product. So the product of 2 invertible matrices is invertible. And not only that, but this theorem tells us a formula for the inverse of AB. Now, I could ask you, you know, just kind of intuitively, do you have any thoughts about what it might equal? And I think maybe there's like a couple of different candidates that seem plausible. It turns out that it's B inverse A inverse. Okay. Well, it seems a little bit weird, but if you think about it, it also kind of looks like a property that we said about transpose. Now, we're not talking about transpose right now, we're talking about inverses, but yeah, doesn't it kind of feel reminiscent of something about transpose from the previous video? So maybe it's not completely unheard of to have the A and B swap places like this in a linear algebra property. But yeah, this is what it works out to. I'm not planning to prove Theorem 6, by the way, but I guess you could definitely verify this for the 2x2 case. Work that out for 2x2. We're actually saying, you know, the stuff that we've been saying on this page is not just about 2x2 anymore. Theorem 5 specifically said n by n. Theorem 6 is also for n by n. Okay. All right, part C. This is the last part of this theorem. If A is invertible, then so is A transpose. And so A transpose inverse, the inverse of A transpose. You take A transpose and then you take the inverse of it, it's going to equal A inverse transpose. That's pretty cool. All right, how are we doing so far? We're not finished yet. We do have one more thing to talk about, but I thought that I would maybe take a moment to pause and just kind of check in. I know this is a pre-recorded video, but we've covered a lot in this video already. We learned how to find the inverse of a 2x2 matrix, and we have one more big thing to talk about in this video, and that's going to be how do you find the inverse of a larger matrix. That's what we're still going to do. But I guess I would say that before we do that, before we embark on that journey, now might be a good place to review everything we've done so far in this lesson. You could pause, you could rewind, you could look at your notes. Make sure that you kind of understand everything up until this point before we talk about the larger matrices. I think that would be a good idea at least. Okay, so let's jump in and talk about how to find inverses more generally. Okay, so I think for this last part, I'm going to go ahead and get us a fresh sheet of paper. So if you're still copying any of this, you might want to just pause the video, copy what you need, and I'm about to move the page away. Okay. So the big thing remaining is an algorithm for finding A inverse not just for 2x2. Now, I do want to remind you that at the beginning of this lesson, when we had the definition of the inverse, one of the first remarks that we said is A has to be square. So when I say it's not just for 2x2, you know, we mean 3x3, 4x4, 5x5. It still has to be a square matrix, okay? Now, I'm going to explain this as an algorithm in 3 steps, and then we'll do an example. Step 1, place the matrix A and the identity matrix side by side to form the rectangular matrix AI. That's step 1. All right, that step is easy. All you have to do is take the, we're assuming that the matrix A is given. So A is given, and you make a larger rectangular matrix that has A with the identity next to it. So I guess what we're making is sort of n by 2n rectangular. All right, next, we row reduce. Wow, I don't know if anyone expected row reduction to come up in this discussion, but yeah, row reduce this rectangular matrix to reduced row echelon form, RREF. Remember how when we do row reduction, we can either get it to row echelon form, which corresponds to a triangular system, or we can get it further into reduced row echelon form. That's where you also have to have, all the pivots have to be 1s, and all the numbers above and below each pivot have to be zeros. So we're going all the way with this to reduced row echelon form. Step 3. If step 2 reduced AI into the form. Now this sentence started with the word if, so this might not always happen, but if this reduced it into the form I, and then I'm going to put a star here, just meaning I and then some other entries, then A inverse is equal to those other entries. Otherwise, A is not invertible. So this is a pretty good strategy. This is a pretty good process, because what we do is we try to find the inverse using step 1 and step 2. And then we have a way of finding out, did we find the inverse, or we may have shown that the matrix is not invertible, and that can also be an answer. So what I'd like to do is, I'd like to do an example with this now that I'll kind of get us started with, and then maybe I'll ask you to do some steps yourself. But I'd like to do an example now, and then after the example, I'd like to talk a little bit about why this algorithm works, because it doesn't really seem obvious. Like, where does this come from? Example first. I'll get it started. And remember, this is the whole point of this is for us to be able to do this on larger matrices. So let's do this with a 3x3. Oh, by the way, this also does work for 2x2. When I say not just for 2x2, this strategy works for 2x2 matrices, 3x3, 4x4, whatever. But I feel like if I had a 2x2 matrix, I would probably use the strategies that we talked about earlier in this lesson. I think for the 2x2 case, those strategies are faster. But for the 3x3 and above case, let's use this. Okay, given A equals 1, 1, 1, 0, 1, 2, 1, 2, 4. Find A inverse if it exists. By the way, I'm going to get this started, but by the way, notice that for matrices of this size, we have not learned what the determinant is yet. I can't check the determinant yet, at least at this point in the course. I can't check the determinant because we only have a formula for 2x2s. So we can't even use that as like a shortcut to figure out whether or not this is invertible. That's okay. We're just going to get started on this algorithm, and the algorithm will tell us whether or not it's invertible. So step 1 says you take the matrix and you put it side by side with the identity, which is 1, 0, 0, 0, 1, 0. Sometimes I've seen some people draw like a little dashed line here if you want, like this. That's optional, but just to indicate that, you know, here's the matrix A, here's the matrix I. So we put them together into one large thing. That's step 1. We're done with step 1. Step 2 is where all the work takes place. We have to do Gauss-Jordan elimination, lots of row reduction steps. I think on my page, this takes, I don't know, 4 or 5 steps. So I'm going to get it started. I think, I'm, you know, looking at this 1 and this 2, and we want to kind of get rid of some stuff down here. So I think a good first step would be, I'm going to add negative R1 to R3. See why I'm doing that? It's going to knock out this 1 in the lower left. So let's just first copy row 1. And I'm not going to make that vertical bar in the middle anymore. You can if you want to. It doesn't really do anything. I'm not changing row 2 yet, so let's just copy it. All right, and we did this to get a 0 here. But how does it affect the other entries? I guess we get a 1 and a 3 and a -1, 0, 1. All right, so I said I was going to get this started, and now I would like you to see if you can finish this. Pause the video, see if you can finish, and then you can check back with me. All right, so this is good row reduction practice because we haven't done any of that lately. Remember, your row reduction steps might be different from mine. We should still all get to the same destination. I added -R2 to R3. So if you didn't do that step, it could still be fine. We just may have seen it differently. That's going to get me... All right, I guess I'm not changing row 1, so I'll copy it. And I'm not changing row 2, so I'll copy it. But what am I doing to row 3? I'm getting a 0, 0, 1, -1, -1, 1. So I did that to get a 0 here. For my next step, I decided to do 2 steps at once. We want to add -R3 to R1. Right, I think that's going to help with row 1. And I also wanted to add -2R3 to R2. So I'm changing row 1 and I'm changing row 2. The only row I'm not changing is row 3, so I'm going to write row 3 first. A lot of times I like to write whatever's not changing. Okay, so what did we do to row 1? We turned row 1 into 1, 1, 0, 2, 1, -1. And what did we do to row 2? We turned it into 0, 1, 0, 2, 3, -2. It's okay to do 2 steps at once like this as long as they're kind of independent of each other, like we were doing something to row 1 and something to row 2, so those were not interacting with each other. And, just be careful. Be careful if you do multiple steps at once. All right, I think I can finish this in 1 step. Look at this. This is almost in reduced row echelon form. The only thing that's bugging me is this 1 up here. If the 1 that I'm pointing at were a 0, then we would have it in reduced row echelon form, because it looks like I have a pivot here, it's a 1, a pivot here, it's a 1, and a pivot here, it's a 1. So everything above and below those leading 1s needs to be a 0. So I think I see what step I need to do to turn that 1 into a 0 is I need to add negative row 2. Add negative row 2 to row 1. Now, could we have done this in fewer steps? I don't know. Maybe. I certainly think you could have done these steps in a different order, and that would be fine. But this is how I saw it. So this gets us 1, 0, 0, and then what does it change the rest of it to? I got 0, -2, 1. And row 2 and row 3 haven't changed, so let's copy them down. All I'm doing is full row reduction to reduced row echelon form. I'm not making any assumptions about whether this is invertible or not. We did it. We got reduced row echelon form because every leading entry is a 1, and every number above and below each leading entry is a 0. And look at that. We didn't we get the identity matrix? I'll put the little line here again. We're done with step 2 because we did reduce row echelon form. Step 3, which you can just barely see at the top, says if step 2 reduced us into the form I something, then A inverse equals that something. So this is the result, is that A inverse equals the 3 by 3 matrix that we found as a result of step 2. Pretty cool. Pretty interesting, I think. I think it's interesting that this gets you the identity. I mean, gets you the inverse. And I also think it's interesting how we started with a matrix that was rectangular that has A next to I, and then you go through all the steps and you wind up with I next to A inverse. It's like the I, the right half of this matrix gradually shifted away from being the identity and gradually got more and more complicated, while the left-hand side of this rectangular matrix gradually got closer and closer to becoming the identity. It's pretty interesting, I think. So that's the problem. I want to talk a little bit about why does this algorithm work. And again, what I'm going to do here might not be a full rigorous proof. In this class, we do some proofs of some things and not everything. But I want to give you just some sense of why does this algorithm work. So I call this a sketch of the proof. Or maybe you think of it as like an outline of the proof, just leaving out some little details here and there that you could find in a textbook. Just more about us and our overall understanding, I guess. So suppose A is n by n and invertible. Let Ej, the vector, denote the jth column of I. We've used that notation before when we talked about linear transformations. So Ej is the jth column of I. For each j, row reducing Aej would use the same row operations used to row reduce Ai. Let me talk about that sentence a little bit. I'll just give you a chance to see it. The steps that we did, you know, add negative R1 to R3, add negative R2 to R3, whatever steps you chose to do. If you had set it up as just A and then one column of I, you would still wind up doing the same row operations. If you're trying to get it into reduced row echelon form, you'd still use the same exact row operations because it's really the A part of it that matters the most. Okay, so the systems AX1 equals E1, AX2 equals E2, all the way up to AXN equals EN, can be solved simultaneously by row reducing AI. Because each one of those systems would use the same row reduction steps, we might as well just do them all at once. Each of the n systems above finds one column of x in the equation, that's a capital X, in the equation AX equals I. Do you agree with that sentence, that here I have n systems, AX1 equals E1, AX2 equals E2, and so on, right? N systems, and I'm saying each one of them would find one column of this larger matrix X. So this is matrix times matrix equals I. By definition, this matrix X must be A inverse. Why does it have to be A inverse? Because AX equals I, and that means X is an inverse of A, the inverse of A. So this was a sketch of the proof. It doesn't cover every detail that a textbook might cover. I guess you could say that one big sketchy part of this is that this seems like it began by assuming that A is invertible. So this seems to suggest that if A is invertible, then the algorithm works. Why is it that if A is not invertible, like why is it that the algorithm can also help us conclude that a matrix is not invertible? Anyway, I left some of those details out there in the textbook, but hopefully this gives like just a little bit more understanding of the algorithm. Also, I like this idea of you have like a bunch of systems that are like matrix vector equals vector, matrix vector equals vector, matrix vector equals vector. And I like the idea that because they have the same row operations, we can solve all of them at once by just row reducing one system. I think that's pretty cool. Okay, so we did it. So we can wrap things up now. So by this point, you know, first of all, you should be good at matrix operations from the previous lesson where we learned how to do matrix multiplication and things like that, transpose, a couple of other things. But now, today, we talked about what is a matrix inverse, how do you verify if something is a matrix inverse, you know, all about the identity. And we spent a lot of time talking about the 2x2 case, and that has a specific formula. We had a summary, and we put a big box around it. But you know about how to find the determinant of a 2x2 matrix. That can tell you whether or not it's invertible. And then once you know that it is invertible, you know how to finish the problem. Like use the determinant and use the other part to find A inverse. So if it's 2x2, I would probably use that strategy from the middle of the video. If I gave you a 3x3 or even a 4x4, you could use the strategy that we did towards the end of the video, where you put A and I side by side and do row reduction. And everybody who's following these lessons should be very good at row reduction by now. Row reduction is kind of a fundamental skill for linear algebra, so practice your row reduction if you need to. All right, so that is it for now, and thanks for watching, and I'll see you next time.